Welcome to our interim presentation.
This project aims to design a drone that maximizes flight range by optimizing the three subsystems within the system boundary: propulsion, frame, and battery. We are not optimizing outside the system, but external factors will impact our optimization. Interactions between subsystems and external factors are shown in the figure. All subsystems have interrelated inputs and outputs that will need to be solved iteratively.
To begin optimization, system-level parameters and assumptions were needed. The drone is a quadcopter that delivers a 2-kilogram package, a minimum range of 10 kilometers. It has a maximum weight of 10 kilograms, and the subsystems have allocated percentages of this weight. Wind and ground effects are not considered, and we assume the drone moves at a constant speed. In this initial effort, subsystems were decoupled to be optimized separately, as shown in the slide. As minimal design work had been completed to this point, some additional assumptions were needed. Maximum allowable weights for the drone and its subsystems were used. Lower than standard air pressure was utilized. The coefficient of drag and frontal area for the package were used, as these inputs will be dominated by the package. Battery energy is from the battery with the most available energy discovered during initial research. Propulsion system dimensions are the average values for all propulsion options considered in this analysis. Propulsion power is the minimum power necessary to move the loaded drone at 25 miles per hour. Current draw is defined as the maximum current for the propulsion systems. All subsystems were optimized using MATLAB's genetic algorithm. This method was selected as it allows for integer design variables representing discrete options. Our design variables are well-bounded, a requirement for using this algorithm. To ensure global optimum results, different creation and crossover functions were utilized to create the initial population and form crossover children.
The goal of the propulsion system is to select the most efficient combination of propulsion elements to optimize their energy usage and to contribute towards the overall system goal to maximize range. The objective function shown here takes in battery energy, motor power, and vehicle velocity to output range. The input constraints of the propulsion system are vehicle gross weight, minimum speed, battery current, and motor power. Some relevant constant values are also air density, vehicle coefficient of drag, and vehicle frontal area. Some of the equations used in deriving the dynamic power of the propulsion system are shown here. Equation 1 shows the thrust required to avoid the quadcopter changing velocity in the vertical direction. Equation 2 shows the max pitch angle that the quadcopter must fly at to zero out vertical velocity and to maximize horizontal velocity. Equation 3 shows the velocity of the quadcopter as a function of the propeller's physical properties. Equation 4 shows the mechanical efficiency relationship between the motor torque input and the mechanical thrust power output. These equations were used to govern a genetic algorithm that chose the most efficient motor and propeller combination from a library of options. The results of the previously mentioned genetic algorithm optimization are shown on this slide. The optimal speed selected was 45.9 miles per hour, resulting in a max range of 32.5 kilometers. It is worth noting that all runs selected the same motor and speed regardless of what creation or crossover function were used. This suggests that the results of the function are a global optimum. It is also worth noting that the chosen motor and propeller weigh less than what was allocated for this subsystem. In further revisions of our model, we will investigate adding these weight savings back into the energy calculations to capture their effects on range.
The goal of the frame subsystem is to select the most efficient frame dimensions and material to withstand the weight of the package and electrical components as well as the forces from the propulsion system while minimizing weight. The design variables for this optimization are the inner and outer dimensions of the drone's three beams, which are oriented in an H shape, as well as their material options. The system is constrained by the maximum allowable displacement of the center beam, the mounting requirements of the motor, and the maximum weight allowed by the propulsion subsystem. Our drone is modeled as an H-frame quadcopter with the battery and electronics centered on top of the center beam and the package attached beneath. To simplify the mathematical modeling of the subsystem, we only consider the forces acting on the center beam as a point load on a simply supported hollow rectangular beam.
For the frame's mathematical modeling, the goal was to optimize its overall weight. We started by keeping the drone stationary in the air, allowing for a simplified representation of the middle beam in the H-frame. Using a simply supported beam model, we set F total equal to the weight of the package and drone components. Then, we used the hollow beam's dimensions, constrained by a minimum manufacturable thickness, to calculate the area moment of inertia. The material's modulus of elasticity determined the maximum displacement, which we limited to 0.5 millimeters. Finally, we used the dimensions to find the volume, and in turn the weight. We applied the von Mises maximum distortion energy criterion to check if the material had yielded, but it did not affect the optimization.
The same optimization approach of genetic algorithm was utilized here. Our first run showed severe variability, which could be due to the number of variables being optimized for, but it did help to narrow down to the two best material options by weight, which were Kevlar and CFRP. We then ran a refining optimization using only these two materials to get the global minimum for the rest of the parameters we wanted to optimize for. As we further refine this optimization effort, we should consider additional insight from the other subsystems to ensure we are coming to the best solution. Since Kevlar and CFRP have the same weight, it comes down to the frontal area optimization to reduce the CD in the second run to determine the best dimensional parameters for the beams. As we continue to add information such as the tilt angle from the propulsion subsystem, our optimization results will continue to improve.
Our third subsystem is the battery package, where we aim to identify a battery configuration that maximizes flight range while supplying enough power to the drone. To do this, we want to maximize our operation time, which is effectively maximizing the energy capacity of the drone. Our design variables are which batteries we're using, as well as how many of each we want to put in parallel with each other. Constraints consist of weight and volume of our package, as well as current and power demands. Here are the key formulas used to mathematically model our battery package, namely the capacitance, the power, operation time, as well as the energy supplied. Some simplifying assumptions are that there is no voltage sag or float. Additionally, our battery operates at constant efficiency, and for safety reasons, batteries can only be connected in parallel with their respective series type, so for us that is 6S or 12S.
As discussed, our subsystem optimization problem will rely on the parallelization of batteries to increase their overall capacity in amp hours while complying to the weight and volume constraints of 6 kilograms and 10 liters respectively. While we expect these values to change upon integration with the other subsystems, they are enough for us to optimize our subsystem in the meantime. To implement this, we employed a simple box stacking algorithm for packaging different batteries together in addition to the genetic algorithm to inform our battery selection. After leveraging the same creation and crossover functions as the previous groups, we received 3 unique outcomes from MATLAB due to the large number of possible battery combinations. From the results, we conclude that the 6S batteries in parallel that we labeled as 4, 14, and another 14 battery are the optimal solution for our subsystem given the constraints that we used. This gives us an operation time of just under half an hour from the derived 67 amp hours this battery package would provide us. Moving forward, we plan to sweep our weight and volume constraints, all informed from the inputs of the other subsystem groups in our team, to determine the best battery configuration given the optimal conditions after combining all the subsystems. Thank you for listening to our presentation, and we'll see you for the final report.